All right, everybody. So what we're going to be doing today is the week 8 lecture 2. So before we do that, I'll just mention that you can see down here you have an exam that is due next Tuesday. That's posted now. If you're looking at this later than fall 2025, then maybe you don't have an exam. Um, all right, but let's get into the lecture. So last time we talked about floating point numbers. And this time, what we're going to be doing is we're going to be looking at the zyBooks exercises for chapter 4. So we should find chapter 4 zyBooks, which is here, and we'll go ahead and jump in. So it starts out with floating point numbers. So I'm going to skip down here and see if I can find anything that looks a bit complicated. Um, well, maybe we'll mention a couple things here too. So when you are kind of thinking about how fractions work in binary, the places to the left of the decimal are powers of 2 with positive powers or 0. So like 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, and so on. If you go to the right of the decimal point, you basically get negative exponents of 2, or you could think of that as 1 over a power of 2. So the first place is the 1 over 2 place. The second place is the 1 over 4 place. 1 over 8, 1 over 16. So those represent smaller and smaller fractions as you go to the right of the decimal place. Okay. So when you get a question like this down here, it says, can you represent a 1/2 using one fraction bit? Yes, because the first place to the right of the decimal is the halves place. So you can. If they say, can you represent a quarter using one fraction bit? The answer is no, because we saw in our picture here that to get to a quarter, you need 2 digits past the decimal point, because the first bit represents a half and the second bit represents a quarter. So you have to get at least 2 of these bits in order to represent a quarter. So the more bits you use, the more precise your fractions can be. I just said yes, even though I explained the answer was no. Could you represent a quarter using 2 fraction bits? Yes. Could you represent a tenth using 3 fraction bits? The answer is no. But again, you can get that by looking up here. So a half, a quarter, an eighth, a 16th. So first of all, there's no tenth here, right? But to get a number smaller than a tenth, you'd have to have 1, 2, 3, 4. The fourth bit would be smaller than 1/10, but it still wouldn't be equal to 1/10. So when they say down here, could you represent 1/10 using 3 fraction bits? I mean, the answer is no, but you need probably a lot. So it says the best approximation would be 1/8 if you had only three fraction bits, which we saw. You had a 1/8 and then you had a 1/16 would be 4 bits. Could you represent 1/9 using 3 fraction bits? No, for the same reason. Could you represent the square root of 5 using 3 fraction bits? Square root of 5, what is that? Right? You could go to like Wolfram Alpha or something. I didn't type in Wolfram Alpha. And you can do square root 5, and it's like 2.23. And it's an infinite decimal. So no, you can't represent it with 3 fraction bits. You need infinitely many bits to represent it, but you can do an approximation with however many bits that you have. Um, so no, you can't, but can't be represented in binary because it has an infinite number of bits. The closest you could get is 2.25, which we saw here. The actual answer is 2.23, so that's how close you can get with 3 bits. All right. Now, we talked about this before in lecture, how to write things in this 32-bit floating point format. And what they have here is basically a calculator. We can type in a number up here, and then we can see the result down here. So if you were to look at that floating point worksheet that we had, you could enter a decimal value and get the output down here. if you want it, right? So like if we put in 48 here and hit convert, then we get this, and that was one of those problems, for example. Um, you can see the result. I guess we can't change it here, but there might be another one. Is there? I guess there's not another calculator to go the other way up here. But let's see here. Let's see if we can understand this. So given the following binary floating point representation, determine the following. So the sign bit is the first bit. So sign bit 0. The exponent bits come next. There's 8. So that's next. And then the exponent in decimal, uh-oh. So we did all this in the worksheet last time. I'm just going somewhere where I can type right now. So we did this in the worksheet, but basically, if you take this here, this 8-bit number, so take 8 exponent bits, what are we going to do with them? We need to, 1, convert to binary, or sorry, convert to decimal. Decimal. So we have, here they are. If you write these out, I'm going to kind of space them. When you have 8 bits, the first one, the first place is 128. The second place is 64. The next place is 32. The next place is 16. The next place is 8, then 4, then 2, then 1. So if you look at the bits versus the places, then the number that we had, which was this, is we see that there's a 1 in the 128th place, and we see that there's a 1 in the ones place. So that is 129. However, that's not actually the real exponent because you have to subtract 127 to get the real exponent. What's stored is what they call the biased exponent. When you write something in floating point format, we have to add 127 to whatever the exponent is. So that means when you go the other way, you have to subtract it. So the real exponent would be 129 minus 127, which is 2. Now, it's possible that this is going to be marked wrong, but they didn't. I was a little bit worried. Significant fraction bits, consider copy pasting, absolutely. Now, those are the bits. Does it want us to add 1 point? I don't know. No, it didn't. So they just wanted us to copy those 23 bits. Normalized scientific notation. So it's 2 to the 2 here because the exponent was 2. So, I mean, if you knew a lot about this, then you could have looked down here, seen the 2 of the 2, and written the decimal there. But what we want is the normalized scientific notation. So we have these bits, right? But you need to add 1 point in order for it to be accurate. Now, do they want this in binary like it is? Let's find out. No. No, they don't. What do they want? What they want us to do is, so they want us to take these bits. So these are the fraction bits. Not fraction, but fraction bits. We need to add 1 point to the beginning. 1 point to the beginning. After we do that, then what we can see is that there's a lot of zeros that don't mean anything. So I'm just going to cut off the zeros we don't care about. So looks like all these are zeros. So we have this. So when you look at this number, we need to convert to decimal. We just have to remember what each place is. So we have 1.001, which in terms of places, obviously this is 1. but then this is the ones place, but this is the halves place. This is the quarters place, and then you have the 16ths place, which is 0.125. So this number, when you convert it, is so 1.001 in binary is in decimal, it's 1.001. The one corresponds to 0.125. So it's 1 plus 0.125, which is 1.1125. So this is 1.125 times 2 to the 2. Okay. Now, in terms of what number is that, you should just jump over to a calculator and we do 1.125 times 2 to the 2. So it's 4.5. 4.5 there. All right. So negative exponents convert the other way. So if you have this number here, which is 125, right? Then if you think about it, if you have an exponent of 125, that's not the real exponent, right? That's the biased exponent. So you have to subtract 127. So 125 minus 127 should give you an exponent of negative 2. And that's what they're asking for because it says times 2 to the question mark, right? So they want to know what the exponent is, negative 2, right? So you have to subtract 127. And then it says the number in base 10 is what? Well, here it says 1 times 2 to the negative 2, right? So 1 times 2 to the negative 2 is 1/4. In the 32-bit representation, the sign bit applies to um, the number, which is the significand, not to the exponent. All right. So I'm going to skip down and see if there's a challenge activity. There is. So let's look at that. So binary floating point format, 4.1.2, enter the decimal equivalent. Oh, okay. So we have to just do the conversion here. So just eyeballing this right here, right? The sign bit is 1, which is, oh, sorry, the sign bit is 0, which means positive. The exponent is this, which is in decimal 128. Now I know that, right? Because I just remember that when we did this on the exponents, right? 8 bits, the first bit is the 128 place. So I can just easily look at this and see that that's 128. But that's biased. So the real exponent is 128 minus 127, which is 1. 1. So what is that? Let's move this out of the way. So the exponent is actually 1 at the end of the day. And then the significand, well, we've got all these bits here. So the 1 point, it's 1.011, right? So what is that? Well, let's do a calculation. 1.011 is, well, let's just copy this from up here. Oopsie. 1.011. So I had to change that. 1.011 is a 1, a quarter, and an eighth. So that is 1.011 is 1 plus a quarter plus an eighth. So you add that all up, oops, eighth. And that's going to be 1.375, I think, right? 1.375 when you add that up. So, this is base 2. This is base 10. So what do we have at the end of the day? We have, so the number is 1. 1.375, right, times 2 to the exponent 1. So it's 1.375 times 2. So you grab a calculator, and it is 2.75, I guess. What? Oh, I did not read the problem. It said, what's the decimal exponent? The exponent was 1. Okay. That makes me sad. We converted the whole number and we only needed the exponent. Okay, sorry. Let's do this again and pay attention. So this time we have this number for the exponent. Boom. Which is what? Well, in terms of places, right? We have a ones place, twos place, fours place. So this is a 1 and a 4. So that's actually a 5, right? But that's the biased exponent. So you actually have to do, whoopsie, you have to do 5 minus 127, which I guess is negative 122, which is an odd thing, but they're not actually making us um, do a whole problem there, but that's a really small exponent. Um, what's the significand as a decimal? Well, we have 1011, which we already did. Isn't that 1.375? I think we just did that a minute ago. Then we have 1001. Wait, enter the decimal equivalent of the following binary number. Oh, we ought to do the whole number this time. Okay, now we got to do the whole process. So what do we got? So the sign is 0. Just delete this. So this can stay. The exponent, actually the exponent's 1, isn't it? Because it's 128. So the exponent is 1, 1, 2, 3, 4, 5, 6, 7, which is 128. The real exponent is 128 minus 127, which is 1. So the exponent is 1. The significand is 1.001, 1.001, which is what? Well, what, like I can do this, we can sort of do this in our head if we're careful. Um, I guess we don't have to be careful. It's 1001, so it's this. One place, 0.125's place. So this is 1.125. So what do we have? The number is 1.125 times 2 to the 1. So that's, I think, 2.5. Wait, no, it's not. It's 2.25 is what it is. But I'll just punch it in here anyway. 2.25. All right. If you're trying to make a 0.375, how would you do it? Well, you think of the bits this way. So how do you make 0.375? 0.375 would be a quarter and an eighth. So that would be for fraction bits 0, 1, 1. 0, 1, 1. Convert the decimal into binary floating point exponent bits. What? Convert the decimal into binary floating points exponent bits. Um, they want us to do the whole process. I'm going to look at this. Expected. Convert the number to binary, ignore the sign. 28 is this. Sure. Normalize. Uh, okay. So this is what I didn't understand. I was like, they want the exponent to be 28, or this whole thing is supposed to be the number 28 in floating point format. They want the whole thing. Now, one thing you could do, jump back up here. There was a calculator. Was there a calculator? Yeah, here there was a calculator. And so over here it's 1.125. 1, 1. Here, this was 1, 0, 0, 0, 0, 0, 1, 1. So 1, 1, 2, 3, 4, 5 zeros, and then 1, 1. 1, 1, 2, 3, 4, 5, 1, 1. So you can use a calculator there to save yourself some effort. Otherwise, you would have to go through the whole trouble that we've done a couple times now. Um, all right, same thing here. You'd have to kind of convert this number into a floating point. Let's just do this one. So it's -7, right? So the first thing you do is, the sign bit is going to be 1 because this one's actually negative. Then we need to do the exponent. But in order to do the exponent, well, we can't yet. We can't do the exponent yet because we have to convert 7 into a floating point format. So 7 is, as a binary number, it's 1, 1, 1, right? So what do we do with that? Well, you have to, what do we got to do? It's 1, 1, 1. We need to write it as 1.11. So 1.11, and we had to move the decimal 2 places, right? Because it was here. On 7, it's 111. And to write it as 1.11, we move it 2 places. So we moved it 2 places. That means the exponent is 2. So the exponent is 2, but I want the bits for the exponent. So how are we going to get the bits for the exponent? We would have to take the 2, add 27 or 127 to the exponent 2. I don't know why I just started syntax highlighting. So we'd have 129. And then or in binary, 129 is, well, we know that we have 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. Putting a 1 at the beginning is 128. So to get to 129, just change the last digit to a 1. So we see that there, they did that for us. Now what we have to do is figure out the significand, which is the 3 bits that go here. But we had them right here, right? We had 1.11. So when you write the significand, it's a 1.11, and then we actually don't need this, right? Um, then the other bits just all fill up with zeros until you get to the end. So to the right of the decimal place, we have 110 because they want 3 bits here. Okay. So that's kind of that. Now we got a lot more sections to do, right? So floating point arithmetic. So they're going to explain certain things to you here. So to add floating point numbers, the exponents have to be the same. So to add 4.3 times 10 to the sixth and 8.1 times 10 to the sixth, you just have to add 4.3 and 8.1, and you get 12.4. The exponents here, 10 to the sixth and 10 to the sixth, stay the same. So you end up with this 1 or 12.4 times 10 to the sixth. That's a correct answer. It's just not quite in the proper scientific notation. So you end up having to move the decimal place over once to put it in proper scientific notation, which means you end up adding 1 to that exponent over there. So let's look for an example of this. So when you add 4 times 10 to the 3 and 2 times 10 to the 3, you're going to get 6 times 10 to the 3. That's proper scientific notation, so we're all fine. When you add 5.4 and 4.1, you just add 5.4 and 4.1. That looks like 9.5. And that's going to be just times 10 to the 5th. Oops, 10 to the 5th. What? Oh, I have an extra, I had an extra, what's it called? Caret in there. All right. Now, when you add these, right, the powers are the same, 10 to the 2, 10 to the 2. You can add them. You get 12.5, right? 6.2 plus 6.3 times 10 to the 2. But the problem with this is that that's not where the decimal place goes in scientific notation. So you got to move that decimal place over one more to there. But if you move it one more place to the left, then this has to go up by one. This is going to be the same thing. So 8.5 and 1.7 is 10.2 times 10 to the fourth. But this isn't quite right in scientific notation. So you got to move the decimal place one point over, which means you have to add one right there. Okay. Now, this is the first one where we have, I think, a little more thinking to do. So if you are doing this, of course, you could just use a calculator, save yourself some trouble. You have 2 times 10 to the 2, and you have 5.3 times 10 to the fourth. Now, you can't add these. You have to write them in the same form. So what you could do is you just have to move one of these, you have to move the decimal place somewhere. So like what you could do is you could say, well, 2 times 10 to the 2, right? Isn't that 200, right? Let's just make sure we know the number. Um, if I move the decimal place from where it is here to over here, then this exponent has to go up. And if I move it over one more place and make it 0, 2, then it would go up again. And you can just check that this is true, that 0.02 times 10 to the fourth is 200 in a calculator. So 2 times 10 to the 2 is 0.02 times 10 to the fourth. And then once it's in this form, these can just be added. So we add these numbers, and you're going to get 5.32 times 10 to the fourth, right? 0.02 plus 5.3. All right. So those are those. You can do the same thing in binary. The exact same tricks, right? So you add in binary, and then if you need to move the decimal place over one, then you can increase this. So same deal. I'll just pick one. We'll do this one. All right. So if we're adding this in binary, then we start on this side. 1 plus 1 is 2, but we rate that as 0, and then you carry the 1. And then you have 1 plus 1 is 2, but you write 0, and then you carry the 1. And then you have, so we have a decimal place here. And then in this column, you have 1 plus 1 plus 1, which is 3. 3 is 1, 1. So you end up with, on this side, 1, 1. So 1.11 times 1.01 is 11, right? So this is our answer. Oops. I said 11, but I mean, it's 3. But this is no good. You have to move the decimal place over one more. So you're going to end up with 1.100. And if you move the decimal place, you have to add 1 to the exponent. Um, what? Oh. Remove trailing zeros from the results. Okay. So, I mean, that's what we got to do here. We'll do one of these others. I guess we'll do this last one. 1.11, 2 to the seventh. No, 1.11, 2 to the seventh. 1.11, 2 to the eighth. So I think we're going to be carrying ones a lot. So I'm going to move this over a little bit. And how would this work? Well, first of all, we can't add it yet because these don't have the same exponent. So you can move this decimal place one place to the left and then add one here. Okay. So that we're doing this last one here. After you do that, we need to make the decimal places line up. So we'll do that. Now we can add. Now, if it makes you more comfortable, we can add just a zero right here. And then we can add these numbers. So we'll add the numbers. What will we get? Well, we got to start over here. So 1 plus 0 is 1. And then the next digit is 1 plus 1, which we write as 0. And then we carry a 1. And then we have 1, 1, 1, which is 3, or 1, or 3 is written 1, 1. So we write 1, and we'll have to carry a 1, and that just moved it to wrong place. And then we have 1 plus 1, which is 2, which you write 1, 0. So you write 1, 0 like that. And the decimal place should stay lined up. So when I add these numbers together, this is what I get. 110.101 times 10 to the, or sorry, times 2 to the eighth. Of course, we got to move the decimal place over. We're going to get 1.0101 times 2 to the ninth. So it's all about lining up the decimal places and making sure that the exponents on the twos are the same. All right. So when you multiply, we have to, um, well, really, we have to do regular multiplication. And the only thing you'll do is that when you multiply the 2 to the 2, for example, and the 2 to the 1, you add the exponents as it says here. And then the rest you use regular multiplication. So this is multiplication like you would do long multiplication when you're learning how to multiply things. So, like what you have here is they did 1 times 1 is 1, 0 times 1 is 0, 1 times 1 is 1. Okay. You go down to the next row, you put a 0 here, and then 1 times 1 is 1, 0 times 1 is 0, 1 times 1 is 1. And then you come down to the next row, you have two zeros. And then you do 1 times 1 is 1, 0 times 1 is 0, 1 times 1 is 1. And then we add up. So you do 1, bring it down. 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And then you end up, there's nowhere to carry it. So we just write it down here. Um, the fact that these ones and zeros didn't line up um, is pretty crappy by zyBooks. Like they're not vertically aligned, right? Like the zero, like this zero should be, this one should be over a little bit. This zero should be over a little bit, right? These line up and these three here, 1, 0, 1 line up. Gross. But anyway, that's actually a little bit easier than addition because you do not have to make the exponents match when you multiply. Um, yeah, but writing it's a little bit tedious. Let's do one of these. Not, well, actually, let's do these. Let's do some down here. Should we? Well, let's do one up here first for practice. So let's say we have 1.1 times 2 to the sixth and 1.0 times 2 to the 3. So these are multiplying. So we got, okay. We'll need a couple spaces over here. And I'll just kind of do that. So first of all, we're going to end with times 2 to the ninth because we multiplied those exponents. Over here, we have to do the long division. So you do 1 times 0. I said long division, but I just mean multiplication here. 1 times 0 is 0. Oops. And then then you do 1 times 0, which is 0. And then you have to come down to the next row. So you're already down here. In the next row, you kind of start with like you know, you start, whoa, you move over one place, and then we do this again. So you do 1 times 1 is 1, and then you do 1 times 1 is 1. Should look like this. And then we got to add these up with the understanding that hold on. So we add these all up, and we're going to end up with 0 and then 1 and then 1. So 110 is what we end up with there. However, you've got to move the decimal place 1, right? Like, so when you do multiplication, right? Like, if this decimal place was 1 over from the left and this was 1 over, then you have to move the decimal place 2 places. So it's here, but we move it 2 places to here. So we end up with 1.10 times 2 to the 9, which actually makes sense because this was 1.1 times 1.0. So of course you get 1.1. Nevertheless, this is what we got. Wait, did we do this one? No, we did this one, right? Wait, what did we do? I guess we did this one. Oh, again, I didn't remove trailing zeros. I didn't remove trailing zeros. All right. Um, so, okay. Let's try these. Oh, I didn't do this. I thought we had to hit start or something. So when you're doing this, what happens? You add the exponent. So 2 to the fourth, 2 to the fourth, the result is going to be an 8. What? This was addition. This was addition. Okay. That's so frustrating. All right. Let's try it again. We'll do this one. 1.0000 times 2 to the 2. 1.001 times 2 to the 2. When you're doing addition, you leave the exponents the same. So let's add these. 0 and 1 is 1. 0 and 0 is, stop moving that. 0 and 0 is 0. We get to the decimal point, and then 1 and 1 is 2, which we write 10. So we add these up, we get 10.001, and then over here we get times 2 to the 2. However, that's not the way you do the answer because this is not scientific notation. So we need 1.001, 0001 We move the decimal place one place, so we have to add one here. So this is 1.001, as you see here, times 2 to the what? To the 3. Okay. This looks very similar. It is, in fact, very similar. So let's change this and change these to 4s. And let's do it all again. So same thing. 1 and 0 is 1. 0 and 0 is 0. I'm going to come over here and I'm going to put like a symbol just to get it out of the way. Um, I'll put it equals. Okay, so 1 and 0 is 1. 0 and 0 is 0. 0 and 0 is 0. Then we have our decimal. And then we have 1 and 1, which is 2, which we write as 1, 0. And then over here, this is times 2 to the 4th. We leave it alone. However, we need to move the decimal place by one place, which means we add 1 to the exponent. Now they want it shows this way with that symbol for multiplication. Okay, let's skip ahead. Let's do one of these. Now, in order to know if this is right, you don't know how many decimal places we had to move um, the decimal. You can guess that we had to move it not at all, in which case it would be 2 to the 5th. You can guess that, and it was right. But if you really wanted to know, you'd have to do the multiplication. So, like this one, we'll have to do the multiplication. So, let's do that. 1.00 times 2 to the 3. Put a couple spaces in front of that. Then we have 1.11 times 2 to the 4. Then I will put a line, and I'm going to put an equals, and I'm going to move that over a little bit more. All right. How does this work? So you do 0 times 1. 0 times 1 is 0. Then you do 0 times 1, which is 0. And then you do 1 times 1, which is 1. Now, it's no accident, but this is 1, 0, 0, and this is 1, 0, 0. That's how it has to be. You go down to the next row. There's kind of a blank space there. I'll put an underscore. And then we start here, and you do 0 times 1, which is 0, 0 times 1, which is 0, and then 1 times 1, which is 1. Again, no accident that that's the same. Now there's two places that we have to move over, and we do this again. 0 times 1, which is 0. 0 times 1, which is 0. 1 times 1, which is 1. And then we add this all up. So you add this all up, and what are we going to get? Well, we are going to get 0 carried down. I'm going to put another equals here. You're going to end up with 0, and then 0 plus 0 is 0, and then 1 plus 0 plus 0 is 1, and then 1 plus 0 is 1, and then 1 carried down is 1. So we have this, but this is 2 decimals over, and this is 2 decimals over. So we have to move the decimal place from here 4 places. If you move the decimal place 4 places, 1, 2, 3, 4, it is going to be here. So we get up with 1.11. And then we add the exponents to get 2 to the 7th. So it's 1.11 times 2 to the 7th. Okay, so that's how those go. You kind of have to do them by hand unless you find a good calculator, of which I don't know of one. Um, but we can do these on Tuesday if people need to. Arrays. Now we're into other stuff. So finally, once you get past the floating point stuff, this should go pretty straightforward because this is going to be like just the concept of arrays. Um, so let's see here. What are we doing? If you want my items 1 to equal 46, and this is your array, then you go to the index 1 and we change this value to 46. Um, that's all we're doing here. Let's jump ahead to number 4. Update my items 2. So we do my items 2 equals my item 0. So we're updating this one. What are we going to put in here? Whatever is in my item 0, which is 68. So these are very straightforward. This one says my items 4 equals. So we're coming down here to number 4. We're deleting it. Uh-oh. We're not deleting it. It says my items 4 equals my items 4 plus 5. So currently, my items 4 is 87. We're replacing it with 87 plus 5, which is 92. There you go. We have some participation activities that I think we can handle, like which assigns element 0 with the value 250. Look at that. Element 0, value 250. So this is all just a review of CPSC-06, honestly, right? Or CPSC-14 if you took that. Um, so I guess the key to this section is that they're talking about 10 elements, but the indices are 0 through 9. So when they say first element, right, first, you have to know that first means element 0, right? So you have to do scores list 0 to get the first element, and then it would be 77. I don't know if they want a semicolon. They did, but they didn't care whether or not I put it there. Um, so that's what you got to do. Assign the second element. What's the second element? Well, that's going to be a 1, right? So that's all we're doing here. If the array had 100 elements, what would be the last element's index? 99, right? They want to make sure you know that. If the array's last index was 499, how many elements? Well, it's one bigger. All right. So there you go. Records. This is kind of the concept of data in a class. So at the end of CPSC 06, we talk about classes, and in CPSC 39, I assume you talk about classes quite a bit. So um, records can contain multiple pieces of data here. So if they're talking about naturally grouped data, so you would group the things that go together for a particular topic. And that's what they want you to think about. So like it says, select the pair indicating a flight's travel. Wait, where are we? Why is this? Um, okay, well, whatever. This is the question, so we'll do this question. Did I skip a question? No. Select the pair indicating a flight's travel time. Um, hours and minutes? I don't know why that's a weird question. Select the group of items most likely to indicate the change provided to a person who pays for a meal. Uh, money? Okay. All right. So this is an example of what it would look like if you were accessing fields from a particular thing. So if you have a record, which is kind of, in Java, we'll have classes, and in C++, we'll have classes or structs. But the general concept could be a record, which I guess maps mostly to a struct. And when you access them, it's going to be by the name of the record, the variable name, and then a dot and the field. So we could call these fields like height, weight, age are all fields inside of the health data record. But you can create, when you create a record like this, what you're doing is um, you're creating a type. So this creates a type called health data, which means later on you would be able to declare a variable of type health data and you could give it a name Emily Dickinson. And you could declare another variable called with type health data whose name was Ralph Emerson. So both of these, Emily Dickinson and Ralph Emerson, they're both health data. That means Emily Dickinson has a height, a weight, and an age. Ralph Emerson has a height, a weight, and an age. So you can change Emily Dickinson's height, Emily Dickinson's age, and Ralph Emerson's age, and those will be stored. And we do those things in Java, fairly often, but you know, you generally do it with other classes, right? So we have public class. This is just an example from my CPSC-06 class, right? You could do another like public class, and I could say, um, but generally we don't want to have multiple classes in the same, um, oops, what do I have? Normally we don't want to have multiple classes in the same file. And it's probably going to complain about that. The public type dumb must be defined in its own file, right? So I don't really want to do too much of this. Where is this? This is Lab 6 Part 2. Here is Lab 6 Part 2 source. So right now there's Lab 6 Part 2 Java. I can create a new class. Um, I guess we could use a record, but actually, you know what? I'm going to create a new class and I'm going to call it dumb. And in there, I'm just going to say there's an int age, uh, int height, int weight, right? So we have dumb now in its own thing. And if I declared these all as public, like this, they're all accessible now. And I can come over here and in my program, right, I can say dumb, John. I guess I'd have to do equals new new dumb. I guess I'd have to do it that way. And then I could do dumb Greg equals new dumb. It's not gonna like this. Why doesn't it like it? Oh, because of this. So I create two new dumbs, me and John, right? And then I can do John dot age equals 67, Greg dot age equals 12. And then I can do system dot out dot print line. And I can do John's age colon plus John dot age, right? And I can do the exact same thing with Greg. And we get John's age is 67 and Greg's age is 12, right? Now I did that in a class. But I could also just do like file new record, and it's going to say, well, what kind of name do we want? And I can go like uh health data, and then you just get a public record here instead of a public class. Um, so not much different. I guess I could delete this. We might be able just to right here put what is it? Record, health data, int, age, int, height, int, weight, like that. Oh, cannot be cast to class. Record component cannot be cast to class. I'm gonna have to put this in here. Where do you want it? I'll put it wherever you want. Okay, nope, it doesn't want it there. I don't want to put it outside the class. I was trying to not using a separate file for it. Just making my life hard here. I just didn't want to put it in a separate file. I shouldn't have to put it in a separate file. uh, oh well, I give up for the moment. Okay. Anyway, forget about where these are declared. Um, we can group our data in a record, right? Just like we can group our record or we can group our data in a class as well. Um, but a record is going to be more limited. So if you want to know like the differences, you could look up documentation, but we could also just say, give a quick explanation of record versus class in Java. And it should give us information about methods, basically. So classes and records are ways to group related data. Classes, general purpose building block, fields, constructors, methods. A record is a special kind of class, mainly to store and pass around data. So, okay. There's not like that much to it. So record when you need to hold data, class when you need like methods basically, and data that changes. Um, back here. So you can just think of this as being the same as what you would normally do with a class. And that's actually it for this section. So I think we're done, right? Like you can get through this now, right? Like record house stats. If you do house stats, house stats is a what? Well, it says it right here. It's a record. House A dot bedrooms equals 5. Is that gonna set the bedrooms to 5? I mean, yeah, that's yeah. Fields within a record should be the same data type. Uh, what'd they do here? Int flow int. No, right? The point, the whole point of making a record or for having a bunch of fields of data in a class is that we want to group a bunch of different data that have to do with a particular topic. Um, they don't have to be the same type. If they had to be the same type, why don't you just stick them in an array or something? Um, so it doesn't make sense to even think about requiring them to be the same type. We'll just use whatever we need. You know, you need some strings in there, you need some floats, you need some ints, whatever, just put them all in. Okay. The next section is 5.1, which means that we're done. So I'm going to go ahead and stop this lecture here. It went a bit long. How do I do this? Yeah. So I'm going to stop it right now. Talk to you guys later.